this lecture we are going to talk about the 8086 microprocessors instruction set, and especially the loop and the string instructions. So at the beginning we are going to focus on the loop instructions, then we are going to move to the string instructions. Let's see what is a loop. A loop is a segment of code or a segment of a program that is repeatedly executed. There are some portion of your program that needs to be repeatedly executed, that needs to be executed sometimes more than one time. So in this case you need to use a loop in assembly programming. And loop instructions are some special instructions that perform some operations, some basic loop operation. You may be familiar with loop. What is loop? You have done that in the high-level programming language. Even we've got them in assembly programming language, which is a low-level programming language. So instead of repeating some code sometimes, for example 10 times, 1000 times, anytime, we can perform this kind of functionality using the loop. So the loop replaces the multiple instructions with a single instruction. So in a single instruction we can perform some instructions together. In assembly language we have three different loop instruction: loop E or loop Z, loop NE or loop NZ. How they how they are performing, how they are executed, and what is the operation of all of them. And this one, the meaning of the loop is just a simple loop, and the format is going to be loop and loop to a label. You need to specify a label as an operand of this loop instruction. And every time when this loop occurs, the value inside the CX register is going to be decremented by 1, and this loop jumps to this label whenever the value of CX is not 0. So if you want this loop to repeat 10 times, you need to assign the CX to 10. Then after each iteration of the loop, this 10 is this value inside CX, which is 10, is going to be decremented by 1. It's going to be 9, it's going to be 8, and then 7, up to it gets to 0. So this loop iterates itself, is going to be repeated until the value of CX is becoming 0. And the loop E or loop Z, which are the same, they are the meaning of them is loop while equal or loop while 0. What does that mean? The format of it is the same as loop, anything of them, and then you need to specify the label. And every time when this loop repeats itself, the value of CX is decremented by 1, and this instruction jumps to this label whenever the value of CX is not 0 and the 0 flag is 1. Otherwise it executes the next sequential instruction. It goes to the out of the loop. And again, for this one, loop NE or loop NZ means loop while not equal or loop while not 0, and the format of it is the same as those loops before. And how it works, how this loop repeats itself: every time when the loop iterates itself or repeats itself, the value of CX is going to be decremented by 1, and it jumps to this label whenever the CX is not 0, the CX doesn't equal to 0, and the value of the 0 flag is 0. Otherwise it goes to the out of the loop. So this is the basic structure of the loop. You need to give a count to the CX. For example, if you want this loop to repeat 10 times, you need to give CX 10, move CX 10, and then this is called the body of the loop. This is the label which we are going to jump to it, and whatever is inside this label is going to be repeated as much as the counter or the loop functionality is specified. So whenever those codes or those instructions are executed, it comes to this point: loop next, come back to next. This iteration is going to be repeated until the value of the CX is becoming 0. Okay, so and you know that, and every time when this loop is repeated or is executed one time, the value of cx is going to be decremented by 1. This is the basic example of loop. For example, we have got move ax 0, move cx 4. Okay, we've initialized our counter to 4. That means this loop in the bottom is going to be executed or repeated 4 times, and inside the label we've named label 1. You can name it as any name you want. So we are saying, just for example, add ax and cx. So what is the value of cx is 4, and the value of 0 is the value of ax is 0. So 0 plus cx is going to be 4. And what is going when this one is executed, the body of the loop is executed, the counter is decremented by 1. Okay, so the cx is becoming 3. It goes to label 1. The cx is not a 0, it's 3, so it comes back to the label. So what was the value of ax? 4 plus 3 is going to be 7. Cx is becoming 2. It comes back again. 7 plus 2 is 9. It comes back again. 9 plus 1 is going to be 10, and the cx was 1, it's going to be decremented by 1. It's going to be 0. When this cx becomes 0, the loop is going to be stopped, and it comes to the other portion of the code, and then the program is going to be stopped here. And let us execute this program. So we are emulating it, and then you go step by step. For the very first step, our program is locating here. So move ax 0, 0 is going to be x. Move cx 4, cx is going to be 4. It comes 4 is not 0, right? So it comes to inside the loop. So add ax and cx, so x becoming 4, and the loop is iterating. It comes to add that 3 to the 4 again. It is becoming 7, and then becoming 9, and then becoming 10. This a is in hexadecimal, which representing 10 in decimal. So now whenever this one is executed, the value of the cx is becoming 0, and the loop goes to outside the loop. Okay, the loop is going to be finished, so it's gonna execute this one, move bx8, and then the program is going to be finished. Okay, okay, in this example we are going to evaluate the loop loop if equal, or loop if the cx is not 0 and the 0 flag is 1. So we are saying ax equals to 0, cx4 and dx4. Let's go. It comes to the label, add ax and cx. So ax is going to be 4 because we are going to add it to with the cx, and the result is going to be stored inside the destination. And then we are saying sub dx cx. What is the value of dx4? And the value of cx is 4, so the result is going to be 0, and the 0 flag is going to be set to 1. So the 0 flag is 1 and the cx is 4. So what's gonna happen? The cx is not 0 and the 0 flag is 1. The loop is going to be repeated. So cx is going to be decremented by 1, and it comes back to the loop. 4 plus 3 is going to be 7, and dx was 0 because we already decreased the cx to dx, and it was 4. 4 minus 4 is going to be 0. So 0 minus 3 at this time, the result is going to be minus 3, and the 0 flag is going to be 0, and the loop is going to be stopped, and it comes to the part after the loop. So the bx, we are adding the we are moving this value to the bx, so the value of ax is becoming 7. And in this example we are evaluating loop ne, and this loop repeats itself whenever the value of cx is not 0 and the 0 flag is 0. Okay, so our program starts here. We are moving those values into those registers, and it comes to this label. So we are adding ax with the cx, and the result is going to be stored inside ax. So 0 plus 4 is going to be 4. So dx is 4, cx is 4, sub dx cx, what's going to be the result? 0. And what is going to be stored inside the 0 flag? 1. Why? Because the result is 0. So at this point we are not going to satisfy the loop NA requirement, so the loop is going to be stopped. So as the result, the value of AX is becoming 4, and it comes back to, to this point, and this data is going to be stored inside the BX. And we are moving to the string instructions, and we can say string in assembly language is just some sequential stored bytes inside the memory or inside the registers, or if they are 8 bits they are called bytes, if they are 16 bits they are called words. So in order to perform or to execute some instructions on those strings which we have in the memory or registers, we need to know those basic instructions, which are move, compare, scan, load, store, and we are going to talk about each of them with example in detail. So in order to understand how the string operations are taking place or are executed on the strings, we need to know the operation of the direction flag. Okay, this is very important. Why? Because the direction flag tells whether the string is going to be read in the auto increment or auto decrement. We know that in 8086 memory, main memory, the locations are holding only 1 byte. So, and any string may compose of or may consist of more than 1 byte. So it can take more than one memory location, and we need to know in which direction we are going to read this memory location. And in order to know that, if we say CLD, clear direction flag, the string or the bytes are going to be read in auto increment. Otherwise, when it is set to 1, the direction flag is 1, so we are going to read the string in auto decrement mode. So the address of the memory location are going to be decrement, and those registers which are holding the offset of the memory location addresses are which are used in the string manipulation are the destination index and the source index, while the source index is used in order to hold the source string operand, and the destination is used in order to hold the destination operand. And we know that the destination index is accessing any memory location through the extra segment register, and the source index is accessing any memory location through the data segment register. Let's go to the instructions, and we are going to begin with the move instruction. Okay, move string. So the move string is going to be written like this one, move s. Okay, so move s, move string, byte or word or double word. If you are moving only a byte, we need to use this one, move byte, move s byte, and move sw for the word and those kind of things. And every time, according to the value inside the direction flag, this the offset is going to be incremented or decrement. Let's go to an example of moving string, and let's see how this example works. Okay, let's evaluate this program and what's going to happen here. Before doing everything, we need to specify the offsets of the the source operand and the destination operand, or the source string and the destination string. So we are saying, for example, move si this value, move di these values. So you know that the source operand is working or is going to be combined with the data segment in order to get the physical address, and the data and the destination index is going to be combined with the extra segment. And we say std, set direction flag, in order to read the string in to read the string inside the memory location in auto decrement. And you are saying move si minus 2 this value, move si this value, move si plus 1, and this one. So those are characters which they are combined together in order to form a string up. So but those values are not going to be stored as they are inside the memory location. Their ASCII code are going to be stored. For example, the ASCII code of A is 61, 62, 63, 64, and we say move cx2. That means repeat this loop 2 times. So at the first time you are saying move sb, that means move string only 1 byte. So where it's going to be stored, we are going to send the data from the source to the destination. So this value here, which is a, is going to be stored in this offset. So the segment value is going to be the extra segment. So and for the second time, the value of the data segment is going to be destination index is going to be decremented by 1. So it's going to be 2221. And what is going to be stored? Nothing, because the value of the source index minus 1 is nothing, and the loop is going to be stopped. Why? Because we've set to this loop to repeat itself only 2 times. But if we say 3, what happens? It comes, the first time is going to be decremented by 1, and the second time is going to be decremented by 2, and this one is going to be stored inside which memory location? 2220. Okay. So but if we say CLD, that means clear direction flag, or the direction flag is going to be 0. Which values are going to be stored inside the destination index, or which we can say that memory location which is specified, which its offset is specified by destination index? This value of the source index and source index plus 1, and we know that those are the offsets of the memory location. And the second instruction is the compare string. So you can say CMPS compare string, whether it's byte or word or double word. So it contains the content of 2 memory locations, whether their address or their physical address are specified by the data segment and the source index, and extra segment and the data destination index. And this is an example. We say move si this value, di is value, in order just to specify the offset of the memory location which contain the data, and we are moving this data to this source and move this data to this destination. So we are just comparing them only 1 time. So nothing is going to happen to the string values, to the characters of the string. Nothing is going to happen to them. As a result, only the flags are going to be set or reset. And now we are comparing those 2 values, and their ASCII code value is going to be subtracted from each other, and the result is, because they are both A and their ASCII codes are 61, and when 61 minus 61 is going to be 0, that means in this case the 0 flag is becoming 1. Why? Because the last result was 0. So and the other flags are going to be set or reset, as we have discussed before, if the result is parity even, or if the result is negative, or stuff like that. And the scan string is just like sca string or sca string in byte or in word. It is the same as compare. Nothing going to be happening with the string values. Only the flags are going to be changed accordingly, such as, for example, if the result is 0 or not. And in the compare instruction, we were comparing the value inside the source index and the destination index, or the value inside those memory location which their offset are specified by the source index and the destination index register. But in the scan instruction, we are comparing that memory location which its offset is specified by the destination index with the AX register. So if you are comparing bytes, we are going to use AL. If we are comparing words, we are using AX. Let's say this example. So we are saying move the source index, this value and this one, and we are saying move AL, B and STD in order to let the incrementation or decrementation of the memory location is going to be specified. So we are saying move this memory location, which its offset is specified by destination index, this value, and we are just iterating this loop or repeating this loop only one time, and we are saying scan string in byte. Okay, scan B. So what's going to happen, it's gonna compare that value with that value. It doesn't compare any value which inside the memory location which its address is specified by, or the offset address is specified by the source index. It just compares the value inside the AL and the value inside that memory location which its offset is specified by the destination index. So as a result, it subtracts the ASCII code together, and the result is going to be something, because 62 minus 61 is going to be 1, so the result is not going to be 0. Okay, the result is not 0, so the 0 flag is 0 in this case. And the load string, so we can say load string and load string in byte or load string in word. What is gonna happen, it loads a string byte into AL or loads a string word into AX. It just copies the data from the memory location to the AX register. If it is a word, it's going to be copied to the AX. If it is a byte, it's going to be copied to the AL. And which data inside which memory location, that data inside that memory location which is pointed by the source index. Okay, so because the data we are moving from, the place we are moving the data from is going to be called a source, so we are going to be pointing that data by the source index register. Let's see this example. Move this value to here, and you are saying move AL A. This A is going to be stored inside AL, but we are saying move SIB, and this data is going to be stored in this memory location which its offset is specified by the source index, and we say the loop is going to be repeated only one time. Whenever we are saying load string in byte, what's gonna happen, the data inside that memory location is going to be loaded to AL. So this value which is inside AL is going to be overwritten, and the B overwrites the A. So the value of the AL, the value inside the AL register is going to be B. And the store instruction, this is just like the load, but in the opposite direction. Instead of copying the data from the memory location to the AX register or accumulator, it stores the data from the AL or AX to a memory location. So when it is a byte, the data goes from the AL to that memory location, but when it is low, the data is when it is a word, it's going to be stored inside that memory location. But in this case, the value of AX is going to be stored in those memory locations. But in this case, when you are using AX or when you are using a word, two memory locations are going to be occupied. So this is the example. We are saying move AL this value std in order to set the direction, and then just repeat one time. When you are saying store string in byte, what happens, the value inside this AL register, which is A, is going to be stored inside the destination. So inside that memory location which its offset is specified inside the destination index register, which is 2222, and that the segment value is the extra segment.